Hi, everyone. Welcome to the first FORCE seminar of the fall semester. Thanks for joining us today. I'm Kara Brugman. I'm a research scientist and outreach coordinator for FORCE. You probably see my name on a lot of emails that I've been hitting you hard with this week. And we also have Kyusei here. Do you want to introduce yourself?
Yeah, I'm Kyusei Tsuno. I'm also the research scientist of the FORCE. I came here last August. Yeah, and almost 1 year have passed since I moved to Arizona.
Wow. Yeah. All right. Well, I just want to remind you that you can see a video of our previous seminars with Sally Jane Tracy, Bin Chen, and Yingwei Fei. Those are all on our YouTube channel. See the address here. The video of this seminar will be posted next week. You can also sign up for our listserv on our website, force.asu.edu/newsletter to get updates. And of course, you can follow us on Twitter, LinkedIn, Instagram. We're posting a lot of pictures now of the construction site since Ichiban is going up. And there's a lot of excitement on those channels. So come on over and follow us. We have 2 more seminars coming up this semester, one by Tim Officer from GSE Cars. That's going to be on October 10th. And then pretty shortly after that, on November 3rd, Jin Zhang from Texas A&M will be giving us a talk. So tune in for those as well. So we did want to give you all a taste of our construction progress. We have already constructed the main portion of Ichiban's frame. I have a couple of pictures here of Ichiban and also of the cylindrical pump. And right now I'm going to hand it over to our lab tech, Logan, who is over at the construction site right now.
Hey everyone, I'm Logan. I'm here with student worker Isaac over at the new FORCE space in the new building. You want to hold this? So behind me, you can see here's Ichiban. Most of it's completed glory. Can you hear me at all, by the way?
Yeah, we can hear you.
Okay. You can see for scale, I am 6'1", so you can generally see how big the RAM was put in. See just how big it is over here. Pumping towers and other various equipment. In the distance behind stuff, you can't really see, but that's where Twister currently is. And then in this brick wall building here, that is where the pressure vessel, unbelievable. I have a space where the lab is going to be, and sort of in this general blank space here for the jet. Yeah, and then upstairs we have a upper area that I believe is storage and various stuff.
Yeah, if you guys, there's a little bit of noise in the background, but for the viewers, where Logan is standing right now, that's where the Dia Jasmine will be. That'll be delivered next summer.
Yeah, let's take a look at this side of the press. So here's the other side of the press. You can see some of the tubing and everything that's been set up for Ichiban at this moment. Everything is still, very much in the works, but it's making a lot of progress. The main construction started this week. I believe the first plate was put up on Monday, if I remember correctly. So, in this short amount of time, we've already made leaps and bounds in terms of progress. Yeah. Anything else you wanted me to show, Kara?
No, I think that's good. Thank you so much.
All right. Yeah, my pleasure.
And also, actually, not only the Ichiban, but also the Twister, torsional press was also actually delivered this Monday, right? It's sort of under the in the crate, right? Still.
Here's the box. That's Twister.
Yeah.
We've got to set up the actual user level deck on Ichiban, and then there'll be a larger catwalk around it. So Twister is recreated for now in place where it'll be installed to protect it from all that steel work. That'll be starting, I think, next week. Yeah, thanks so much, Logan.
All right, yeah, my pleasure.
All right, Matt, we'll hand it over to you to share your screen, and Kyusei will give you a little bit of a formal introduction.
Yeah, I'm very glad that we could invite Dr. Matt Whitaker of the Stony Brook University as an research assistant professor. And he obtained a PhD in Stony Brook. And after the several experiences, like the research career in Japan as well, in the Ehime Geodynamic Research Center as an assistant professor. And now, yeah, he came back to the Stony Brook. And he's in charge of the beamline in the National Synchrotron Light Source and in the Max PD beamline, and also beamline in APS sector 6 PM. And yeah, today he will talk about using in situ X-ray diffraction and imaging to study material under pressure. So thank you, Matt, and you can go ahead.
Okay, great. Thank you very much. Yeah, so I'm going to talk a little bit about some of the pretty cool and exciting stuff that we do at the 2 multi-anvil end stations that we run out of Stony Brook. So just to continue a little bit with the background information on me, if it comes up here. There we go. All right. Yeah, so I am a brisk young 44 years old as of a couple weeks ago. I have been a New York resident my whole life, going to college upstate and then getting my PhD down here on Long Island. And after I spent my whole life in New York, I moved to Matsuyama in Japan at the GRC. As Kyusei had just said, that's actually where I first met him. It must be 14 years ago now, almost. And one thing that was very clear while I was there is that everything is a little bit smaller than I'm used to. So you can see here, this is the street that I lived on. This is a two-way street, and my arm span is the same width as the street. So sometimes that got a little bit terrifying. My daughter was born over there, my elder spawn, Emiko. She is now going to be 13 next Friday, so this is a little bit old as far as the pictures are concerned. And now, since we've moved back to the US, we actually have a couple more in the brood as well, who are in first grade. So again, these pictures are a little bit outdated, but you'll see them show up again later, I'm sure. In my free time, which is very little, but I am the singer in a rock and roll band and also in a heavy metal band. So those are what I tend to do in my free time. And I pretty much sustain myself strongly on a diet of caffeine and Archer memes. So hopefully some of you can appreciate that. And now I'll dive right into what we're actually going to talk about today. So we have 2 beamlines that we administer out of Stony Brook University through what used to be Compress and now has been taken over by SEAS, which is the new organization that oversees the management of geosciences at synchrotrons in the US. And we operate 6BMB at the Advanced Photon Source, which is currently shut down. That's a white beam beamline. And we also operate Max PD, which is a monochromatic beamline at the National Synchrotron Light Source 2 that is currently active and where I spend the majority of my time. So that is what we're going to be talking about a little bit today. So just to give you a little bit of information about the alphabet soup that you're going to see, MaxPD stands for Multi-Anvil X-ray Powder Diffraction, and this is a partner user program at the XPD beamline at NSLS2 that was sponsored by Compress, but now SEAS and Stony Brook University, and it supports users that are studying Earth, analog, novel, functional, and other materials under extreme conditions of high pressures and temperatures. Compress was the Consortium for Materials Properties Research in Earth Sciences and just ended its 2-decade plus tenure last week, or 2 weeks ago, sorry. And SEAS has since taken over, and that is Synchrotron Earth and Environmental Science, and SBU is Stony Brook University. So I want to talk a little bit about pressure in relatable terms first, so that we can all be on the same page as to exactly what we're talking about. Pressure is force divided by area. And what that means is that if you have a block that has kind of a flat aspect ratio, and you lay that block flat on the ground, it's going to give you a certain pressure. But if you stand that block on its end, even though it's the same weight, it's going to give you a different pressure because there's a different amount of cross-sectional area that's coming in contact with the ground. So you exhibit a much greater pressure when it's stood on its end than when you lay it flat. And that's the same principle behind the reason we wear snowshoes in the winter, so that we can distribute our weight more evenly across the surface of the snow and not break through the snowbank as we walk across it. Conversely, a 100-pound woman in stiletto heels exerts 20 times more pressure on the ground than a 6,000-pound elephant does. This is primarily the reason I stopped wearing stiletto heels, because I'm much larger than a 100-pound woman. And it's also very difficult to find them in men's size 16. So that was something that I had to give up early on. So to talk a little bit about the pressure that we feel every day, the air pressure around us is 1 atmosphere by definition, and that's about 1 bar worth of pressure. So if you hold your arm out in front of you, you're going to feel 1 bar worth of pressure. And if you take your other hand and give yourself a tight squeeze on the arm, don't leave any marks because I don't want to be responsible for that. But if you give yourself a tight squeeze, you're only adding about 0.2 to 0.4 bars worth of pressure, so not even 50% more. Now, if you can imagine that you're given, all right, now forget that guy. The Rock, yes, The Rock is a more recent and relevant character. If you get a bear hug from The Rock as tight as he can, you're going to add about 5 to 7 bars worth of pressure. And if Bruce Lee were still around and you managed to anger him and he kicked you square in the face, you would be exhibiting or experiencing 25 to 30 bars of additional pressure. And it only takes 12 bars to break bones. So that's a pretty extreme amount that you're going to be experiencing. So now as we move to not quite as relatable terms, the pressure at the bottom of the Mariana Trench is about 1,100 bars, so 1,100 times atmospheric pressure. If you go to the core mantle boundary, the pressure is 1,350,000 bars. And at the center of the Earth, it's 3,600,000 bars. So 3.6 million times atmospheric pressure. So when we study things at high pressure, that's what we're talking about. We're replicating the conditions of the Earth's interior. And there is a matter of scale of these experiments as well. Just for reference, 1 gigapascal here is 10,000 bars, which is the unit that I was using previously. So when we want to replicate some of these conditions, we have the piston cylinder apparatus, which is capable of achieving pressures of up to about 3 GPa and about 1,600 degrees centigrade. And the sample size is relatively large. It's 50 to 500 cubic millimeters. The multi-anvil press, depending on if you use tungsten carbide anvils, which is the standard, or sintered diamonds, which are much more expensive, generally runs with a maximum of about 25 to 30 GPa and 3,000 degrees with a sample size of 1 to 15 cubic millimeters. And if you use the sintered diamond anvils, you can get more than double the pressure range pretty regularly with a slightly lower temperature and about 10 times smaller sample size. The diamond anvil cell, of course, can go to 2 to 300 GPa without much of a problem, and you can hit temperatures of about 5,000 C, but if you can take a look there, we're talking about thousandths of the size of a sample that we would have in the multi-anvil. And with theoretical calculations, you can do just about any pressure and temperature range that you desire, but your sample size is on the order of a unit cell, so it's something that is considerably smaller than any of the experimental techniques. So when we talk about some of the multi-anvil techniques that are available, we call them the large volume press. And it doesn't seem like all that much, but it is when you compare it to some other things. So here in Japan at the GRC, we had a 2,000-ton press, and this is my friend Haruka standing next to it. We also had a 3,000-ton press in the same room, and there's me standing next to it. And you can see our heads are the same distance from the bolts that hold the presses together above us. So you would potentially think that they're about the same size. However, I should reveal that I'm 13 inches taller than Haruka. So you can see the 3,000-ton press is significantly larger and is built into the floor, much the same way that Ichiban will have an elevated platform around it so that people can access the actual active zone.
Hey.
Here, I'm sorry, what? Oh, okay. So here we can see some of the cell assemblies that go into the multi-anvil press. And again, we can get up to about 30 GPa and 3,000 degrees centigrade. But the sample volume, again, is very small. You can see that it shows up as just a speck in the palm of my hand there. And there are a couple of different geometry types that we're going to talk about today. This diatype geometry is what we have available at the 6BMB beamline. And this is a very simple cubic assembly that has 6 anvils that come together around a cubic cell assembly where your sample is centered in the cell. And everything squeezes together and you can form pseudo-hydrostatic pressure that way. The Kauai type geometry, as you can see here, is significantly more complicated. We have 8 anvils that come together around an octahedral cell assembly. There are lots of bits, pieces, and parts that need to come together in order to make that experiment happen. But those things are put together. The anvils are assembled around the sample in the center. You put it in the press, you squeeze everything to death, and then when you pull it out, everything is crushed up like you see at the bottom right. Now, the Kauai type geometry, again, is more complicated, but it allows you to exert more force on the sample and achieve higher pressures than you can in the dia. So now we'll talk a little bit, very briefly, about diamond anvil cells. Now, diamond anvil cells are a completely different beast in that the entire apparatus is shown in Sayaka's hand here. So it's something that can be held in the palm of your hand. And when you separate it, you can see at the center of both halves of this apparatus are the diamonds that give it its name. So the 2 diamonds at the sample, as you can see on the palm of her hand, is too small to be able to see. The diamonds come together and compress around a gasket which contains the sample material that you're interested in, and you can squeeze those together and reach much higher pressures because, again, pressure is force divided by area, and in this case the area is very small, so it requires relatively little force to be able to produce high pressures. And this regularly can go up to 200 to 300 GPa and 5,000 degrees Celsius with laser heating. But again, the sample volume is very small. So one of the things that are the concerns when you deal with multi-anvil versus diamond anvil cell experiments, I'm going to illustrate here. And you can see this is a data set that I collected over a decade ago. And it plots the elastic modulus and the P&S wave velocities of a material versus its density. And you can see it forms a very clear and consistent temperature relationship there. There is similar data that was collected in the diamond anvil cell. And what I'm going to do is I'm going to take the smallest error bars that are on the diamond cell data at the left, and I'm going to take the largest error bars from the diamond cell data on the left, and I'm going to plot them on my data on the right. And as you can see here, the error bars for a single data point in the diamond anvil cell cover my entire data set here. So that concludes the shade that I will be throwing at the diamond anvil cell community right now, and I'll move on and focus predominantly on the multi-anvil experiments. So again, talking a little bit about what we had already mentioned, the dia geometry is much simpler and the Kauai is more complex, but the dia is limited in its achievable pressure range, and the Kauai is capable of much higher pressures. So both systems are very good for studying materials under extreme conditions of pressure and temperature. And in order to study rheological properties of Earth materials under these extreme conditions, there were new experimental apparatus that were needed. And this led to the development of the deformation dia, which is now very widespread and commonly called the D dia. And this was originally designed and pioneered at beamline X17B2 at NSLS-1. So the diagram at the right shows that you can compress the entire thing together as you push the top and bottom together. The wedges come in from the sides on the 45-degree guide block. So you produce a pseudo-hydrostatic pressure on the sample. But then you can drive the differential rams, top and bottom, separately, and you can use that to deform the sample as well. So you can make it shorter in one direction. And those experiments help you understand the strength and the rheological properties of the material. So why do we care about that? It's a difference between elasticity and plasticity. In elastic deformation, you have a sample sitting at ambient conditions, and then you add pressure to it. And the force that you're adding is the same in all directions. And this is the sample under stress now is smaller, as you would expect it to be, because it's been compressed by the force. When you release that stress, the sample reverts to the same size and shape that it was before. But under plastic deformation, that's not quite the case. You have a starting sample that starts under those same ambient conditions, but you have pressure that's higher in one direction than another. More force is being applied in one direction than the other two directions. And what that means is when you release the stress afterwards, the sample is changed. It's not in the same shape and not the same properties as it was when you started. So this type of apparatus is what allows you to be able to study that. So when we talk about the high pressure deformation apparatus, we have the simple dia configuration that we have here, where we have our sample, and this gets put into our D dia, and again we can advance the differential ramps on the top and the bottom and deform our sample and study it that way. And in the D dia geometry, we have a relatively limited pressure range where we can go to about 10 or 12 GPa max easily. It can be extended a little bit further, but it becomes a much more difficult experiment. So how do we get to higher pressures? And that's where the D-Kawhi geometry comes into play. We can definitely reach higher pressures with that, but what is the maximum of the pressure that we can achieve in these type of experiments? And that's something that we set out to be able to understand. So very similarly to the D dia, we have the pressure come in from below, where we have the entire guide block squeezed together to add pressure to the sample, and then we can drive the top and bottom pistons separately in order to deform it. And that's basically how this system works. So first we did the deformation Kawhi geometry in the development and commissioning of the DT cup, which is the DT10. The 10 stands for 10 millimeters, which is the edge length of the cubic anvils that are used in the multi-anvil device. This was a collaboration between Stony Brook University and the University College London. And this Kawhi type geometry deformation apparatus did in fact lead to a higher pressure range than the D dia. And we were able to get it up to 18 GPa and 1600 K with X-ray imaging and diffraction. And we were able to achieve a strain of 60%. So as you can see with the X radiographs that are shown at the lower left, as you move from the left to the middle to the right, that's increasing the amount of strain that is on the samples. So we were able to shrink the whole thing by 60%. And this was something that we had commissioned and published just before the NSLS-1 shut its doors in 2014. However, one of the issues that we ran into with this device is that we were limited in the maximum load because the 10 millimeter hard anvils risks damaging the steel press jaws that are forcing everything together. So again, pressure is force divided by area. So we needed to scale it up in order to make that make higher loads achievable. So we scaled it up to the DT25, which again, 25 just means it's 25 millimeters on the edge of the cubic anvils that we use. And this is a picture of the inside of the DT25, where we have the piston exposed on the left. We have these three little tripartite wedge pieces that we put in the hole space there in order to form what would be a surface that's very similar to a regular 111 geometry Kawhi press. And we can then again actuate the top and bottom anvils separately. So inside the Max PD hutch, we have the press, the 1,100 ton press that's shown behind me here. And as you get from the left to the right, you get closer and closer to your fate. You can see that there is the hole cut in the middle there. That's where the X-ray beam enters. And there is a symmetrical hole cut on the backside, which is where the X-ray beam exits the sample. So how do we utilize the X-rays in these experiments? Well, on the bottom left here, we have a diagram that shows that we have the incoming beam coming from the right side, and it enters the sample, which is at the center of the pressure medium there, and then the X-rays exit through the left side, and the diffraction cone is then collected downstream from the sample. You can see here that the X-ray beam is actually shot in between the anvils. So it goes right in between the anvils to be able to hit the sample. And then we get the information out the backside by sending the diffracted beam through sintered diamond anvils, which are transparent to the X-rays, as opposed to the tungsten carbide anvils that we use on the front side that just eat all of the X-rays up. So here again is a picture of the press with the incoming X-ray beam coming from the right. And if we look all the way on the right here, we have the X-ray beam going in and entering the sample cell assembly and hitting the sample. And then the exiting X-ray beam first hits the scintillator, which gives us an X-radiographic image of the sample. And then the diffraction goes around the scintillator and hits the large area detector in the back. And that's where we collect our X-ray diffraction data. So what do we see from this type of data? Well, in the X-ray images of the sample, we can see that in this particular cell assembly, there are two samples present. The one on the left is the bottom sample, and that's just under 1.2 millimeters in length. And then there's the top sample that is just over 1 3/4 millimeters in length. This is at 7 GPa and 1200 degrees C. Once we add the deformation to it and we start driving those top and bottom anvils forward, we deform the sample, and we can see that both samples together are now shorter than the shortest sample was at the beginning of the deformation. So we were able to achieve, again, 60% total strain. The imaging system has been optimized and the resolution is improved such that 1 pixel is exactly equal to 1 micron. So it's a very easy conversion to make when you're measuring these images. And the DT25 currently has been tested up to about 23 GPa and 2700 Kelvin, but it's important to note that this is not the maximum conditions that it can achieve. And we've been able to achieve, as I said, 60% total strain. So this is a pretty exciting result that we have here. So one of the things that we did recently using the DT25 is looking at the process for forming stronger metals through processing. And this is something that I did with Darren Pagan at Penn State. This is he and an undergraduate student, Lucas, that came with him. We did some pretty cool and interesting experiments. So I'm going to kind of give you a little bit of a breakdown of what that's all about here. One of the things that we're looking at in particular is to understand better the forging process. And forging is something that goes back till time immemorial almost, where you have blacksmiths that are making nails and spikes and horseshoes and things like that. And the process of forming the metals is what happens during forging. It also occurs today, not just with a hammer on an anvil, but also in large-scale industrial processes like shown here, where you're forming a large building ballast. So the basic gist of what forging is you have an impact force that's directionalized, and you have a large hot metal piece that you're then impacting in order to change its shape, its structure, recrystallize it, and form a particular set of properties that you're looking for in order to make that material hold up to the conditions that you want it to. So one of the things that we're interested in doing, obviously, is optimizing this process so that we can maximize its reproducibility, so that every time we hit it the same way, we get the same results. We also want to make sure that we are getting the highest strength that we can out of these materials with a very low failure rate, because as you can imagine, if you're one of the people that's inside a building that's held up by one of those ballasts and it fails, that's probably going to ruin your day. So we want to make sure that we understand exactly what's going on here. We also want to enhance the sustainability of the process, where we minimize the amount of energy that it takes in order to do this. And we also want to reduce the amount of waste that's left over after this process is completed. So the problem that we run into is that we can see things before, we can see things after, but we can't observe the process as it's occurring. We can only see the products. And that's where the synchrotron comes in particular, the max PD end station that we have at NSLS2. So we can take the sample to, in this instance, 10,000 bars of pressure, 1 GPa, and we can collect some full field X-radiographic imaging of the iron sample. And that image is shown here at the left. Just in case you're not used to looking for things like this box here shows the outline of what the image is. So I'm going to flash it back and forth a little bit so you can get used to seeing it. The iron part is darker than the surrounding materials, but that is a sample before deformation. We then added a 12% strain field before we did the heating process. And after we did the addition of the pre-strain, you can see that the sample has significantly changed its dimensions, and it's become 12% shorter in the process. And that's exactly what we were looking for in the experiment. So now, what does X-ray diffraction show us? We have the incident X-ray beam coming in and hitting the sample, and the X-rays are then scattered off of the atoms in the crystals in that sample. And when they're scattered constructively, that's what will form the peaks that we see in normal diffraction patterns. Since we're randomly orienting the crystals in the sample and we're doing a full two-dimensional diffraction pattern, those peaks end up showing up as rings on our detector, which is shown at the right. So we have our sample that starts off at 1 bar, and it gives us a set of characteristic rings. Now we're going to add pressure. The sample is going to become smaller, which leads to the rings getting bigger. in monochromatic beam, which took me a minute to really wrap my brain around, but that is the case because you're increasing the 2 theta, which is characteristic of a decrease in the despacing between the atomic planes. So now, once we're at high pressure, we're going to add that deformation field. And those perfect circular rings then begin to deform into ellipses, where the despacings between the atoms, the atomic planes, are smaller in one direction versus another. And this is what we're looking for in these experiments. So it's a little bit difficult to see with the naked eye because it's relatively low pressure and the deviations are relatively small. But that is exactly what we see in the data that we collect from this experiment. So to show it a little bit clearer, what I'm going to do is take the images that we see, the X-ray diffraction images that we see at the left, and we're going to do what's called a cake plot, which basically you slice the diffraction pattern around, much like a cake, around its center, and you unfold it. And what will happen is when you have a perfect circle on this diffraction pattern, it will become a straight line in the cake plot. And that's what we see here. In particular, I want you to focus on these 2 lines that are shown here. Right now, at high pressure, they are perfectly straight lines, but once we institute that deformation step, you can see that those straight lines become very clear wiggles. And those wiggles are what are a measure of the ellipticity of the rings once the deformation step is done. So you can see here that it goes very wiggly right there. So this is exactly what we were looking for in the experiment. So to go back to the impetus for the whole thing, the problem that we were looking to do, or looking to solve, was being able to see the process as it's happening, and we were able to do that successfully. We can observe those processes as they occur at high temperature, pressure, and strain, and we're able to repeatedly reproduce the pressure, temperature, and strain conditions of forging and some of the textures that are observed in the finished product, so we know we're on the right track. And what we found, just as a general rule, is that the grain growth, as expected, is faster and easier at lower pressures and higher temperatures. Recrystallization is slower at high pressures and lower temperatures. And this was just submitted a couple weeks ago to Scripta Materialia. What's very exciting about this, too, is it opens up more doors for study, because it's not just the process of forging that we can look to understand, but we can also look at things like metal rolling, where a larger sheet of metal is rolled between those 2 rollers in order to form sheets of metal, which can be have very specific properties because of the orientation of the crystals. It also can form large pipe fixtures, like you see at the right here. One of the other things that I'm very interested in looking at is being able to reproduce some of the properties or conditions that are found in metal extrusion, where we have locally very high pressures and temperatures associated with the area where the metals are forced through the dies that are used in the extrusion process. So this is something that we're looking to continue, and it's a very exciting new avenue that we're exploring at the Beamline. So now I'm going to go back in time a little bit. This is back into NSLS 1 days, and we're going to talk a little bit about some of the work that I did with, he at the time was a postdoc at Brookhaven Lab, and he's now a faculty member at Farmingdale College just down the road here. We were looking to synthesize a potential superconductor that is a pnictide material, and I call it LaMenPo, but it's lanthanum manganese phosphorus oxygen. It's very difficult to synthesize this material at ambient pressures, and it's extremely sensitive to contact with the atmosphere. So what we did was develop an experimental protocol for fast compression. We took the sample cell that was prepared under an inert atmosphere and sealed in a glove box. We brought it over to the Beamline, and we took it to the press, and we shattered the glass ampule that it was in, put it in the press, put the anvils around it, and then we loaded the cell from 0 all the way up to 55 tons in less than 60 seconds, which is extremely fast for a dia, considering that the maximum load that we normally put on the dia is 60 to 65 tons. This was extremely fast. We were able to successfully manage the environmental contamination of the material and prevent it completely. We also were able to pull off all of these experiments without ever once breaking a cell assembly thermocouple or anvil. So I'm very, very pleased about that. One of the things that we found is that whether it's doped with fluorine or hydrogen, there's very little change in the crystal parameters. And regardless of the doping, the sample does remain an insulator. So pressure does in fact have a substantial effect on the crystal structure of the material, and there are significant changes to the C to A ratio and other parameters that are shown in the plots on the right. So hydrostatic pressures show that about 12 GPa, there's a transition to metallic behavior, but under non-hydrostatic conditions, like would be seen either in a deformation experiment or typically in a diamond anvil cell, that pressure transition happens closer to 20 GPa. So the takeaway from this is that LaMenpo goes through an insulator to metal transition at about 12 GPa. The material never becomes superconducting regardless of the doping or the pressure. But this technique of rapid compression can be used for other environmentally sensitive samples, which is something that we've been doing pretty consistently over the last, wow, I hate to date myself and say 10 years, but it's almost that now. So that led directly to another type of study that we did at 6BMB at APS. So this is my former student, Melinda, and something that she was interested in and had NASA funding for was to study the origins of a mineral known as tissuntite. And this is one of many mineral phases that are only found in meteorites and impacts. And it's essentially a clinopyroxene with plagioclase composition and vacancies making up the rest of the crystal structure. And it was theorized to form from a mescalinite precursor or a melt and a very narrow range of pressure and temperature. But it was, at the time, never successfully synthesized, and there was no refined structure for it. So how do we investigate the formation of the phase? Well, we proved previously that we can beat the press up by going to very high load very quickly. So what happens if we do the same thing but with temperature this time? So we did relatively quick compression to its peak load. And then once it was at its load, we did a spike heating protocol where we took it from room temperature up to about 1500 degrees Celsius in less than a second. And we then would quench to room temperature, depending on the experiment, after 5 to 60 seconds. And we were able to monitor all of this with X-ray diffraction as it was going on. We could decompress and recover the sample. And basically, this experimental protocol is very much like a reverse impact event. Whereas in an actual impact event, you see a pressure wave that comes in and enters the sample. And that pressure wave is followed by a temperature wave of heating that comes behind it. In this case, what we're doing is we have a sample that's confined under high pressure, and we send in a temperature wave, and then the thermal expansion of the materials in there cause the pressure wave to follow it. So in a sense, it just happens in the exact reverse order that you would see in a natural impact. And we were able to successfully synthesize tissuntite. So this was, we were able to do it first time. So we were very happy with that. We could explore a little bit about the compositional space and some of the pressure and temperature space that this material might form under. And we were able to determine that not only was it the first synthesis of it, but this Goldilocks zone that they like to refer to was significantly lower pressure than it was previously assumed, which helps bracket some of the formation conditions of these meteoritic materials. So defining the phase space and structural refinement of the phase is still an ongoing effort, and we're expanding both the pressure and temperature range and working on compositional differences. But the initial results suggested that the P and T formation between 4.5 to 10 GPa and higher than 1000 C are necessary conditions. And the kinetics also suggest that the precursor material must already be amorphous. If you start with solid or crystalline plagioclase, it does not go to completion. And we published this back in 2018. And this spike heating technique has been made available for other experiments and collaborations where we're looking at perovskites, oxynitrides, diamondoids, and other types of materials. So moving on to more recent things that we've done synthesis-wise at the Max PD end station, we were able to reveal a new nickel-lead phase. And in this case, the lead flux requires a minimal sample path length because, as you can imagine, when your sample is made of the same material that you're using to absorb the X-rays so nobody dies, it becomes a little bit difficult to be able to see through the sample. We created a boron nitride double cup to decrease the sample diameter, and we used split gaskets that we worked with Kurt to develop and use, and that helps us simplify the diffraction pattern. And that's pictured at the right there is Alex Tamaris, who at the time was a PhD candidate. She's the first PhD that graduated from experiments done at the NSLS2, so that was pretty cool. You can see here that as we increase the temperature, the lead melts out, and then after we have the thermal quench, we see that there's a new phase that forms. As we decrease the nickel content and increase the main group valence, we can see the structural changes that are shown at the top right here. And the bottom left, they appear a little bit darker than I had intended, but it shows the change in size and shape of the sample as the experiment goes on. So, and this information was published in JAX in 2021. So one of the other things that we've done very recently is the synthesis of transition metal carbides. That's been a very large thrust at the beamline. And we have, the reasoning behind this is that there is a unique mixture of metallic, covalent, and ionic bonding in these materials. And they have a host of useful properties, from radiation shielding to catalysts to hard materials. They have very high hardness, chemical stability, and very good thermal and electrical conductivity. So multi-anvil press allows us to have a path for recoverable bulk synthesis of these materials. So we had a sample cell in particular containing manganese and carbon, and we loaded it into the max PD press. And the in situ X-ray diffraction, shown at the right, shows the formation of new peaks when heating the sample. Now, these recovered samples can then be analyzed using in-house XRD, and they did the structural refinement, and it was indexed to manganese 2, carbon 0.8, which is highly stoichiometric, as it were, with a space group shown here. And this is the first reported manganese carbide of this type, and this work is part of Paul Marshall's thesis. He's the guy that's shown in the circle in the picture on the lower left. And this is currently, we're iterating a version of this manuscript right now. So now I'm going to go both backwards and forwards in time and talk a little bit about my first love, which was acoustic velocity measurements. So there's a reason that I love these, and that they're very near and dear to my heart. They directly measure several different physical properties in a material without the need for a pressure standard. And they provide important ground truth benchmarks against which other techniques and other data sets can be compared. It actively measures the shear properties of materials where other techniques don't. The diffraction that we collect gives us the unit cell volume. The unit cell volume is a direct measure of the density of the sample at all of the conditions of pressure and temperature. The X-radiographic image of the sample gives us the sample length at all of those conditions. And the acoustic measurements that we make using ultrasonic interferometry give us the P and S wave travel times. When we have the length and the time, that yields the velocities, which means that the density and velocities yield the bulk and shear modulus, which we then have directly measured at every condition of pressure and temperature without the need for fitting, which is super cool. So this is just an example of the X-radiographic imaging evolving as we go from 0 to 12 GPa. You can see that the sample gets consistently shorter as we go, which is exactly what you would expect to happen in the experiment. The ultrasonic signal is sent into the sample from a transducer on the back of the anvil. The signal travels the anvil through the buffer rod and into the sample, and the reflections on those different surfaces are shown in the diagram at the lower right. And the way that we determine the travel time is we physically overlay the reflections for R1 and R2, which is the buffer rod sample surface and the backside of the sample. And that gives us the two-way travel time for the P&S waves in the sample. So we can then, I want to give you a little bit of a math warning, because if you're anything like me, that when you start to see a lot of these equations pop up, your eyes glaze over and you start contemplating your own mortality. So we can then take all of those data and fit them into the finite strain equations. And there's a lot of different equations in math here, but basically what we're looking for are these parameters that I have circled here. And there is going to be the bulk modulus and its pressure and temperature derivatives, and the shear modulus and its pressure and temperature derivatives. And once we have this information combined with all of the data that we collected, we can then model a material's behavior under any set of pressure and temperature conditions that we need. So this is just an example of that on epsilon iron silicide, where we have the P and S wave velocities at the top left shown as a function of pressure, and the elastic moduli on the top right. We were able to fit these data and determine the elastic properties of this material for the first time, and using this type of ultrasonic experiment at high pressure. And this is what I did for my dissertation at Stony Brook. So there were a couple of issues that I always had with the ultrasonic experiments, and we wanted to try to think of ways to make it a little bit better. So the problems that we ran into were that there were separate control systems not integrated into the experimental controls. So at the time, back in 2009, it required 4 different computers to be able to collect all of the data that you needed for a single experiment. And doing that as a single person got a little bit hairy at about 4 o'clock in the morning when you were there by yourself. So because of this also, we had no ability to script, automate, or coordinate experimental data collection. So at the time, multi-anvil based ultrasonic systems in the US took about 150 to 200 seconds to be able to collect their 1024 waveform acquisitions. Spring 8 in Japan at the time took 45 to 60 seconds in order to collect this. So these relatively slow collection speeds limited the types of experiments that we could do and the types of measurements that we could make. So at the time, they also relied on a single detector, which gave us no information on potential differential stresses. So we came up with the diascope system. And what this did was integrate everything into the EPICS control world, where we could control the waveform generator, the ultrasonic interferometer, the X-ray diffraction, the X-ray imaging, all through one single source. And we were able to put it all together so that it communicated properly and we were able to automate it. So when we built this system, it collects a full set of ultrasonic data in under a second. It can measure processes like melting and phase changes as they occur. Again, this goes back to something that I talked about earlier with the metal forging, where we can see the before and the after, but not the during. Now we're able to see the during because of the speed of this. So this also makes full use of the full suite of detectors that we have available at 6BMB, which is 10 elements of an energy dispersive detector arranged in a circular array. And again, full integration into experimental EPICS-based controls. And it's now 100 times faster than it was when we published it back in 2017. So this is just a look at some of the things that we did with it originally. Some of the initial studies as we were commissioning this was studying the elasticity of iron-rich olivines. And you can see here in the top middle that the diffraction, the peak position of the diffraction changes with respect to iron content, which is exactly as you would expect. And we also see that the P and S wave travel times change as well with the iron content of the olivine, which again is exactly as you would expect. The travel times get longer as the sample gets slower. So we also have done some work on the elasticity of phaolite, and this was published a couple years ago in the European Journal of Mineralogy. We can see that the sound wave velocities as a function of pressure are shown here in these two, on the plot on the left. And the unit cell volume of the phaolite sample is given as a function of pressure at all temperatures in the plot on the right. And we were then able to take some of this data and use it to determine something about the composition of the Martian mantle. And what we found here is that the optimum olivine contents that are determined by adjusting the P-wave velocity of a Martian mantle model leads to a roughly 0.6 to 0.66 component of olivine in the Martian mantle. So this is an exciting application of this system. One of the things I saw Taryn in the audience earlier, so I'm going to talk her up a little bit while we're here. We've done some experiments that begin to study the acousto-elastic effect of San Carlos olivine. And this study is designed to investigate the stress-induced variation in the elastic wave velocities, which is known as the acousto-elastic effect. And this has not previously been investigated. So this uses the diascope system with a hybrid acoustic and deformation cell assembly. And there's uniaxial deformation experiment with ultrasonic acoustic velocity measurements combined with elastic plastic self-consistent modeling to interpret the X-ray diffraction data. And no one has done this outside of Taryn before. So this is a completely new field that she's walking into, and she's killing it, if I can say so myself. The response to loading definitely differs for compressional and shear wave velocities. And there's a lot going on here, but we basically are trying to determine the acousto-elastic constants of the material. And the longitudinal waves and the shear waves are measured in the sample using ultrasonic interferometry. And then the data is collected, the X-ray diffraction data, in addition to the ultrasonic interferometry, and all of this is plugged in through the control system of EPICS, as I mentioned earlier, for the diascope system. The images give the sample length, and then we have the travel times, and the EPSC modeling lets us know a little bit about what's going on in the sample as the deformation continues. And you can see in the top right diagram there that as you move around the circle of detectors, there is a marked difference in the position of the despacing of the peak. And that's exactly what we want to measure when you start to see. That's that ellipticity that starts to form that we talked about earlier. So, as part of Taryn's master's thesis and in a paper that she published in 2021, she was able to determine some information about the acousto-elastic effect in San Carlos olivine, which she is much more qualified to talk about than I am. So again, I'm here mainly just to brag about the good work that she's done. And I'm sure that she would be more than excited to discuss any of this with you if you have any particular questions for it. So some of the present and future collaborations that we have going on at the Beamline, we're looking to continue the expansion of the user base, both within and beyond the Earth and Planetary Sciences, with material science, engineering, solid state chemistry and physics, and also national defense. So we're continuing with the synthesis and phase relations of novel intermetallic compounds and the applications of differential pumps to apply uniaxial strain fields for phase transition and synthesis experiments. We're continuing our work on novel transition metal carbides and pushing to extend the pressure range that we get in the press as much as possible. It's close to 30 GPa as we can get. So we also just recently went through the fabrication of a new DT25 module for integration of acoustic velocity measurements, which were not possible in the existing module because there was no place to put any wiring or get any signal out. So this is something that we're doing in partnership with the now defunct Compress, NSLS2, the Nuclear Science and Technology Department at BNL, and the National Nuclear Security Administration through Los Alamos National Lab. This new module also will allow for other measurements like electrical conductivity and acoustic emissions and things like that, but that's a little bit further down the road. So some of the salient questions that we have is why should this be done at NSLS2? And one of the things obviously is that it opens up relationships for collaborations between Brookhaven Lab and Los Alamos Lab. But also the high energy monochromatic X-ray beam that's available at XPD is really ideal for the diffraction and imaging data that we want to collect in these experiments. We typically use a 67 keV beam, which is capable of penetrating a lot of things that lower energy beams are not. So we can do these acoustic measurements directly integrated through the EPICS control, as we proved with the diascope. And the high pressure system at max PD can generate more than 3 times the pressure that's attainable in the Paris-Edinburgh press at HPCAT, which is where the collaborators from Los Alamos currently conduct some experiments. And the expertise that's available at NSLS2 is ideal for these studies. And by that, I mean this guy. So one of the things that we had to do is figure out how we're going to contain these radioactive materials in the case of a rupture at high pressure and temperature. So our engineer, Ed, was able to design a Lexan shield that prevents material escape in the event of a cell rupture. And it has been fabricated, delivered, and tested. You can see it fits nicely in the press there. And we were able to test the effect on scattering and imaging, and it is negligible. So we are very happy with the results that we have here. This is on August 2nd, we had our new DT25 module that was delivered and installed into the press. So we are also having an exciting period of new things showing up, just like you guys are in Arizona. So we were able to put this into the press, and we were able to test the integrity of the shielding with it. We installed the new module, did some low load testing, main load testing, the current capabilities, and a mid-range load press, so that we are in good shape and ready for the commissioning experiments that will begin in the next beam cycle. We also rotationally aligned the press and module and reinstalled the slit system. We're ready to begin the pre-purchase testing of the acoustic equipment with the Data Science and Systems Integration Group at Brookhaven Lab, or at NSLS2 at Brookhaven Lab. And we're ready to go forward on that. And we're going to run some, hopefully within the next 6 months or so, some test acoustic experiments on some analog samples. And I wanted to close up real quick with kind of a little bit of a perspective about where force fits into this picture that I've tried to paint a little bit today. Force obviously is it's a sample synthesis factory. You can make just about anything with the various pressure devices that you have there, which is really exciting. The ability to have different environments of pressure and temperature, and the ability to make and study samples that are larger, I think is something that's really critical that we have not had before, which is definitely a very exciting way to go. And some of the questions that I think Force will start to be able to answer as things go forward is, how does this larger sample size affect the properties that we observe in an experiment? If we only have, 1,000 crystal grains versus 100,000 crystal grains, how does that affect the properties, that we see as far as the strength and rheology of the material? How do the synthesis conditions play a role in the measure properties? Because we've seen that if you synthesize your sample at 5 GPa versus 10 GPa, even if you're doing deformation at, say, 8 GPa, you're going to get different results from those two things. So force is a key, I think, to begin to answer some of that. And one of the other things that I look forward to being able to compare and ground truth is how well some of the offline experimental results that you get there will match some of the online synchrotron results that we get. And that will open up the door for a lot of potential experiments to be conducted offline using the apparatus that are available at Force. So if you guys have any ideas for experiments that you would like to do, I just put out a quick advertisement that the deadline for the beam time proposals is September 30th. So it's coming up in a couple weeks, but we're more than willing to hear it and help you submit a proposal if you want. And there are a lot of people that need to be acknowledged for a lot of the work that we have done here, and they're shown on this screen here. So thank you to everyone. If you happen to be in the Long Island area, this is a shameless plug right here. Over the next couple of weeks, we got some shows coming up, so it should be a good time. And this is my obligatory closer of the kids as they look more similarly today as opposed to the ones that I showed at the beginning of the talk. So thank you very much for listening, and hopefully I haven't bored you too much.
All right, thank you so much, Matt. That was a great talk. And it's probably the best introduction to pressure and contextualizing it that I've ever seen. So thank you for that.
That's the best compliment that I've gotten. Thank you.
And we've got some applause from the audience. And does anyone have a question for Dr. Whitaker?
I've got one.
Chat. Yeah, go ahead, Tom.
So in the Tisentide study, Chima suggested this Goldilocks zone. How well was the upper pressure constrained in those experiments? The idea that it's a pretty low pressure mineral is not exactly consistent with the interpretations of the pressure from the rocks, rocks themselves. How tightly, or how did you constrain the upper pressure on it?
Without overstepping too much, I can tell you that 10 GPa, we were able to make Tisentite. 12 GPa makes something else.
Okay. How well was the sample characterized afterwards? Because one of the things I'm interested in is from the work that Shima did, we have some pretty good idea of what the chemistry is, but I'm really curious to how much, if these are supersilicic pyroxenes with silicon and octahedral coordination, but I don't know if anyone's really looked at that. You know?
Yeah, so I know some of the post-sample processing you did. So I know that she had sent some samples to you. So you may actually be better equipped to answer some of that question than I am.
Yeah, I don't have any data that can answer that yet, but it's something that should be looked into to see if the silica content in these things could maybe be used as a pressure scale or something.
Mm.
So there was talk at NetSoc. There's an anorthite composition version of this too that they're calling jadidic anorthite or something, or anorthitic jadeite. But it's basically the same sort of thing, but with a calcium analog. But there's some really interesting problems there, I think. And to me, the most interesting thing is are we putting silicon in octahedral sites, and could that be used to estimate pressure? Anyway,
I think that's something that going forward as we continue through the project, I think that we'll start to be able to say something more about than we can right now. We have started expanding the sample compositions. So the first one was, I think AN60. We also have done some experiments on AN40 and AN80. So as we start to put those together, we'll start to be able to see some of that.
So is Melinda there at NSLS?
She is not at NSLS. She is at Brookhaven Lab now. She has a postdoc in another department.
Okay.
She's got beam time with me in December, though.
All right, thanks, Tom. All right, we are 4 minutes past the hour, so if someone has a burning question, we can go ahead and ask it. Otherwise, we can leave it there. And thank you so much, Matt, for your great talk.